There's a point of light in the constellation Virgo that looks, to the casual observer, like nothing more than a faint star. You'd need a decent telescope to see it at all. It registers at about magnitude 13, which means it's roughly 600 times dimmer than the faintest stars your naked eye can detect on a perfectly dark night. By all appearances, it's unremarkable. Just another pinprick in the cosmic dark, one among billions. But appearances, as we so often discover in astronomy, can be profoundly deceiving. That faint point of light carries a designation rather than a name, 3C273. And what it actually represents is so extraordinary, so utterly beyond the scale of normal cosmic objects, that when astronomers first understood what they were looking at, it fundamentally changed our conception of the universe itself. Because 3C273 isn't a star at all. It isn't even close. It's a quasar, and that single quasar, shining with the luminosity of approximately 2 trillion suns, outshines the combined light of every single star in its host galaxy, all 100 billion of them. It does this while occupying a region of space smaller than our solar system. Imagine compressing the light output of 1,000 Milky Way galaxies into a space that would fit comfortably between the Sun and the orbit of Neptune. That's the kind of object we're dealing with. Tonight we're going to explore these cosmic lighthouses together. We'll journey back to the moment of their discovery, understand the physics that makes them shine so impossibly bright, and contemplate what they reveal about the early universe, a time when the cosmos was wild and young, when galaxies collided more frequently, when vast quantities of gas swirled through space waiting to fuel the most luminous objects the universe has ever known. So settle in. Get comfortable. Let's begin with a story about a February night in 1963, when one astronomer stared at a photographic plate and realized that the universe was far stranger, far larger, and far more magnificent than anyone had dared to imagine. The night Schmidt couldn't sleep. February 5th, 1963, Pasadena, California. The offices of the California Institute of Technology, where the afternoon sun slants through windows overlooking a campus that has, over the decades, become synonymous with some of humanity's greatest astronomical discoveries. In one of those offices sits Maarten Schmidt, a Dutch-born astronomer who has spent the better part of several months puzzling over an impossible spectrum. He's looking at a photographic plate, a small rectangle of glass, about an inch long and 1/3 of an inch wide, that had been exposed to light gathered by the enormous 200-inch Hale telescope at Palomar Observatory. On this plate are recorded several dark lines, the spectral fingerprints of the mysterious object known as 3C273. And these lines make absolutely no sense. Schmidt knows his spectroscopy. He's spent years studying the light from celestial objects, learning to read the language written in wavelengths and absorption lines. When you spread starlight into a spectrum, you see distinct patterns, the signatures of hydrogen, helium, and other elements absorbing specific wavelengths as that light passes through the star's atmosphere. These patterns are as recognizable to an astronomer as a familiar face. Hydrogen, in particular, produces a beautiful series of lines called the Balmer series. Every astronomer knows this pattern by heart. But the spectrum of 3C273 shows lines that don't match anything. Not hydrogen, not helium, not any known element. For weeks, Schmidt has been staring at this plate, trying different combinations, different possibilities. What if it's some exotic element? What if there's an error in the observation? What if the object itself is so strange that it's producing emission lines no one has ever seen before? It's frustrating, it's maddening. Radio astronomers had precisely located 3C273 using a clever technique involving lunar occultations, watching as the moon passed in front of the radio source and noting the exact moment it disappeared and reappeared. This gave them a position accurate enough to match with optical observations, and what they found looked like a star, albeit one with a curious jet of material extending from it. A star with a jet already seemed strange enough, but this spectrum, this was something else entirely. After lunch on that February afternoon, Schmidt sits down at his desk. He's been invited to submit a paper to the journal Nature, and he needs to make sense of these observations. He slides the photographic plate into the viewer once more. 4 prominent lines stare back at him, along with a 5th line in the infrared that his colleague Beverly Oak had found using the Mount Wilson telescope. 5 lines that refuse to make sense. And then something shifts in his perception. Sometimes the answer to a puzzle isn't found by looking harder at the details, it's found by stepping back and seeing the whole thing differently. Schmidt notices something about 3 of those lines. Their spacing, the way their intensity decreases from red to blue. There's a pattern there, a rhythm that feels almost familiar. His mind makes the leap. What if those aren't unknown lines at all? What if they're perfectly ordinary hydrogen lines, the Balmer series he knows so well, but shifted? Not shifted by a small amount, the kind of shift you might see from a star's motion or rotation, but shifted dramatically, all of them moved together toward the red end of the spectrum by the same proportion. He does the calculation quickly, his pulse quickening. If you take the standard hydrogen spectrum and shift every wavelength by 16%, you get exactly what he's seeing on this plate. Exactly. The fit is perfect, but 16%. Schmidt leans back in his chair, the implications crashing over him like a wave. A redshift of 0.158. He knows what that means. Thanks to Edwin Hubble's work decades earlier, astronomers understand that distant galaxies show redshifts, because the universe itself is expanding, carrying those galaxies away from us. The amount of redshift tells you how far away something is, and a redshift of 0.158 means that 3C273 is racing away from us at roughly 30,000 miles per second, 16% of the speed of light, which means it's not nearby, not even close. It's approximately 3 billion light-years away. The full weight of this realization settles over him. For an object to be visible at all from that distance, to be detectable by telescopes on Earth, despite being separated from us by an almost incomprehensible gulf of space and time, it must be extraordinarily, impossibly luminous. Not star bright, not even galaxy bright. Something brighter than entire galaxies. Schmidt's wife would later recall that he paced up and down their home that evening, unable to contain his excitement and unable to fully process what he'd discovered. Because this wasn't just about one mysterious object in Virgo. If 3C273 could be this far away and this bright, then other quasi-stellar radio sources, the other mysterious star-like objects that had been puzzling astronomers, might be similarly distant. The implications were staggering. He goes to find his colleague Jesse Greenstein, who had been working on another puzzling object called 3C48. "Jesse, come and see what happened," Schmidt says, showing him the spectrum and the shifted hydrogen lines. Greenstein looks at the data and then at 3C48's spectrum, which had been equally mysterious. If Schmidt's interpretation is right, then maybe. They work through 3C48's spectrum together. Sure enough, it too shows hydrogen lines, but shifted even more dramatically, indicating an even greater distance and an even more prodigious luminosity. The universe has just revealed that it contains a class of objects no one had anticipated, objects that challenge every notion of what's physically possible. Within weeks, the scientific community would begin to absorb the shock. Within months, hundreds of these objects would be identified, their distances measured, their properties catalogued. They would come to be called quasars, a contraction of quasi-stellar radio source, though we now know that not all of them are strong radio emitters, and Schmidt's February revelation would mark a turning point in astronomy, opening a window onto the early universe that remains, more than 6 decades later, one of our most powerful tools for understanding cosmic history. But on that February evening, as Schmidt paced his home and contemplated his discovery, the fundamental question remained tantalizingly unanswered. What could possibly produce that much light? What kind of cosmic engine could generate the power of 2 trillion suns from a region no larger than a solar system? The answer to that question would take time to emerge, and it would involve some of the most extreme physics in the universe: supermassive black holes, accretion disks heated to millions of degrees, magnetic fields strong enough to launch jets of material at nearly the speed of light. But we're getting ahead of ourselves. Let's slow down and explore step by step what makes a quasar shine with such impossible brilliance. What makes a quasar shine? The feeding frenzy. Picture a black hole. Not just any black hole, but a supermassive one, a monster with a mass millions or even billions of times that of our Sun, sitting at the centre of a galaxy like a dark heart around which everything else orbits. Most galaxies we now know harbour such objects. The Milky Way has one, Sagittarius a star, weighing in at roughly 4 million solar masses. Some galaxies have black holes that make ours look modest by comparison, tipping the scales at billions of solar masses. Now picture that black hole not in isolation, not quietly sitting in darkness, but actively feeding. Material, clouds of gas, streams of dust, occasionally even entire stars falls toward it, drawn inexorably inward by gravity's relentless pull. But here's the thing about falling toward a rotating black hole. Material doesn't typically plunge straight in. It has angular momentum, a tendency to orbit, and so it forms a queue, a spiral, a disk of matter waiting its turn to cross the event horizon. This is an accretion disk, and it's one of the most violent, energetic structures in the cosmos. The disk spins. It has to. Angular momentum doesn't just disappear, and as it spins, particles at different distances from the black hole orbit at different speeds. The inner regions close to the black hole whip around much faster than the outer regions. Think of the planets in our solar system. Mercury completes an orbit in just 88 days, while Neptune takes 165 years. The same principle applies here, but on a scale and at speeds that make planetary motion look positively leisurely. This difference in orbital speeds creates friction. Particles in the inner disk are trying to orbit faster than their neighbours, just slightly farther out. They bump into each other. They collide countless times per second in a chaotic dance of matter under extreme gravitational stress. And friction, as we know from everyday experience, generates heat. Rub your hands together and you feel warmth. Multiply that friction by unfathomable amounts, concentrate it in a region around a supermassive black hole, and you get temperatures that soar into the millions of degrees. At these temperatures, matter doesn't behave like the solid, liquid, or gas we're familiar with. It becomes plasma, a state where electrons are stripped from atoms, creating a churning sea of charged particles. And this plasma glows. It doesn't just glow dimly like a heated piece of metal. It radiates across the entire electromagnetic spectrum, from radio waves to infrared to visible light to ultraviolet to X-rays. The inner regions of the accretion disk, closest to the black hole where temperatures peak, shine primarily in X-rays. The slightly cooler outer regions emit optical and ultraviolet light. The energy output is staggering. A typical star like our Sun converts mass to energy through nuclear fusion in its core, following Einstein's famous equation E equals mc squared. But fusion is actually rather inefficient. Only about 0.7% of the mass involved in fusion reactions gets converted to energy. The rest remains as the mass of the resulting helium and heavier elements. An accretion disk around a supermassive black hole, by contrast, can convert between 10 and 40% of infalling matter's mass into pure energy. Think about that for a moment. Drop 1 kilogram of matter into the accretion disk of a supermassive black hole, and you might get 10 to 40 times more energy than you would from fusing that same kilogram in the core of a star. It's the most efficient engine we know of in the universe, short of matter-antimatter annihilation. This is why quasars can shine so brightly. They're not relying on the comparatively gentle process of nuclear fusion spread throughout a star's volume. They're tapping into gravitational energy, the energy that's been stored in matter's position in the gravitational field, and converting it to radiation with brutal efficiency. A supermassive black hole with a mass of, say, 1 billion suns, consuming just 10 solar masses of material per year, can produce a luminosity that rivals or exceeds that of an entire galaxy of hundreds of billions of stars. And it does this from a remarkably small volume. Observations of how quickly quasars vary in brightness give us a way to estimate their size. If a quasar brightens or dims over a period of, say, a few days, then the emitting region can't be much larger than a few light days across. Why? Because if it were larger, light from different parts of the region would arrive at different times, smearing out any variations and making them undetectable. This is the light travel time argument, and it's remarkably powerful. When we apply this reasoning to quasars, we find that their brightest emission, the optical and ultraviolet light, and especially the X-rays, comes from regions that are often smaller than our solar system. Some quasars show X-ray variability on timescales of hours, suggesting that the X-ray emitting region is only a few times larger than the black hole's event horizon itself. Imagine standing, hypothetically impossibly, at a safe distance from a quasar's accretion disk. You'd see a disk of light so bright that it would dwarf everything else in the galaxy. The billions of stars surrounding this central engine would be utterly overwhelmed, invisible against the blazing glare of the quasar. Looking at the disk edge on, you'd see layers of different colours, the inner regions glowing blue-white with the fierce heat of X-ray emission, the middle regions shading through all the colours of visible light, the outer regions glowing in infrared as they gradually cool with distance from the central black hole. The disk wouldn't be smooth or uniform, instabilities would ripple through it. Bright spots would appear and fade as particularly dense clumps of material spiraled inward. Magnetic fields, tangled and twisted by the disk's rotation and the black hole's spin, would thread through the plasma, sometimes organizing the chaos into structures, sometimes adding to the turbulence. The physics here is extraordinarily complex, so complex that even with the most powerful supercomputers, astronomers struggle to model all the details accurately, because it's not just gravity at work here, it's also magnetohydrodynamics, the interaction between magnetic fields and electrically conducting fluids. It's general relativity, the warping of space-time near the black hole that affects how particles move and how light propagates. It's radiation pressure, because the intense light from the inner disk pushes outward on infalling material, sometimes limiting how fast the black hole can feed. It's a rough-and-tumble region, as one astronomer memorably described it, where multiple extreme physical processes all operate simultaneously. And yet, for all this complexity, the basic picture holds. An accretion disk around a supermassive black hole can explain the luminosity of quasars. It can explain why they're so bright. It can explain the spectrum of light they emit. It can explain the variability we observe. When Schmidt's discovery in 1963 demanded an explanation for objects with galaxy-scale luminosities, the scientific community initially struggled. Various theories were proposed. Perhaps quasars were relatively nearby objects whose redshifts weren't cosmological. Perhaps they were powered by some exotic new physics. But as evidence accumulated, as we measured the masses of supermassive black holes in nearby galaxies and confirmed their existence, the accretion disk model emerged as the clear winner. By the 1980s, the idea that quasars were powered by supermassive black holes had become well accepted. Direct observations of black holes in nearby galaxy centres, including our own, confirmed that the necessary objects existed. Observations of active galactic nuclei, the less luminous cousins of quasars, showed the same physics at work but at lower power levels. The pieces fit together. And here's something remarkable to consider. Most, perhaps all, large galaxies probably went through a quasar phase at some point in their history. Our Milky Way, peaceful and relatively quiet today, with its modest 4 million solar mass black hole sipping material at a trickle, was likely once a quasar billions of years ago, blazing with the light of 1 trillion suns. The central black hole was there, just as it is now. But back then, vast quantities of gas were available to feed it. The galaxy was younger, still forming stars at a furious rate, still rich in the raw material that black holes need to power their brilliance. Over time, as we'll explore more deeply later, that fuel got used up. Star formation consumed much of the gas. The black hole itself devoured its immediate surroundings. The quasar faded, dimmed, eventually going dark. What remained was the galaxy we see today, with its black hole quiescent, occasionally flaring when a stray gas cloud wanders too close, but never again reaching the frenzied luminosity of its youth. Quasars, in other words, represent a phase of galaxy evolution. They're not fundamentally different types of objects. They're galaxies caught in adolescence, in a wild period of growth and activity that most galaxies pass through and then leave behind. And because that phase happened primarily in the early universe, because quasars were much more common when the cosmos was younger, they serve as beacons that illuminate that distant past. They're time capsules, messages sent to us from an era when the universe was dramatically different from what we see around us today. Which brings us to perhaps the most profound implication of quasar studies. They allow us to look back in time. They give us a window onto cosmic history. And understanding that requires us to think carefully about light, distance, and the strange relationship between the two in an expanding universe. Ancient light. Windows to cosmic history. Light travels fast, roughly 186,000 miles per second, fast enough to circle Earth's equator more than 7 times in a single second. But the universe is vast, and even at this tremendous speed, light takes time to cross cosmic distances. Light from the Sun takes about 8 minutes to reach Earth. Light from the nearest star beyond our Sun, Proxima Centauri, takes 4.2 years. Light from the Andromeda Galaxy, our nearest large galactic neighbour, takes roughly 2.5 million years to reach us. This creates a remarkable situation. When we look out into space, we're also looking back in time. The light entering your eyes right now from distant objects began its journey long ago, and the farther away something is, the farther back in time we see it. This is what astronomers mean when they talk about look-back time. When we observe a galaxy 10 billion light-years away, we're seeing that galaxy not as it is now, but as it was 10 billion years ago, when the light we're currently receiving first began its journey toward us. Quasars, being among the most distant objects we can observe, offer us views of the very early universe. When Maarten Schmidt calculated that 3C273 was roughly 3 billion light-years away, he realised that the light from that quasar had been travelling through space for 3 billion years before reaching his telescope. We were seeing 3C273 as it appeared 3 billion years ago, when the universe was significantly younger than it is today. That's profound enough. But 3C273, it turns out, is actually one of the closer quasars. As telescopes improved and surveys expanded, astronomers found quasars at ever greater distances. The redshift of quasars, that telltale stretching of wavelengths that initially puzzled Schmidt, can be used to determine not just distance but look back time. A quasar with a redshift of 1 is seen as it was roughly 8 billion years ago. A quasar with a redshift of 2, about 10 billion years ago. The relationship isn't quite linear because the expansion rate of the universe has changed over time, but the principle holds. Higher redshift means looking farther back into the past. And astronomers have found quasars with truly staggering redshifts. Quasars with redshifts greater than 6, meaning we're seeing them as they were when the universe was less than 1 billion years old. Quasars at redshift 7 and beyond, shining in an era we call cosmic dawn, when the first stars and galaxies were just beginning to form. The current record holders have redshift around 7.5, showing us the universe when it was merely 5 to 700 million years old, less than 5% of its current age of 13.8 billion years. Think about that for a moment. The light from these most distant quasars has been travelling through space for more than 13 billion years. It began its journey when the universe was in its infancy. It has crossed an expanding cosmos, been stretched to longer wavelengths by that expansion, finally arriving at our telescopes to tell us about conditions in that ancient epoch. Every photon that reaches us from these distant quasars is a messenger from deep time, carrying information encoded at its emission. And what do these messengers tell us? They reveal that quasars were not evenly distributed throughout cosmic history. Instead, there was a peak, a quasar epoch, when these objects were far more numerous and luminous than they are today. Surveys of quasars at various distances show that quasar activity peaked when the universe was roughly 2 to 3 billion years old, about 20 to 25% of its current age. At that time, there were many more quasars per unit volume of space than there are today. The most powerful, most luminous quasars existed primarily in that era. As we look at more recent times, closer to the present, the number of quasars drops off steeply. Why? Why were quasars more common in the early universe? The answer lies in the availability of fuel. In the early universe, galaxies were still forming, vast quantities of gas that hadn't yet condensed into stars-filled galactic centers. When that gas fell into the gravitational wells of supermassive black holes, it powered brilliant quasars. Additionally, galaxies collided more frequently in the young universe because they were closer together and because there were more small galaxies that hadn't yet merged into larger structures. These collisions and mergers funneled additional gas towards central black holes, providing even more fuel for quasar activity. As the universe aged, several things changed. Much of the available gas got locked up in stars. Star formation, which was extremely vigorous in the early universe, consumed raw material that might otherwise have fed black holes. The black holes themselves ate through their immediate surroundings, and galaxy collisions became less frequent as the universe expanded and structures became more separated. All of these factors contributed to a decline in quasar activity. The epoch of peak quasar luminosity passed, and we entered a more quiescent cosmic era. Today, most supermassive black holes in galactic centers are quiet, or only mildly active. Our own Milky Way's black hole, Sagittarius A star, accretes material at a rate that produces relatively weak emission. Far too faint to qualify as a quasar. We see occasional flares when a gas cloud or an unlucky star passes close enough to be partially consumed, but these are brief and modest compared to the sustained brilliance of a true quasar. Most nearby galaxies show similar behaviour, Their central black holes are there, just as massive as ever, but starved of fuel. This gives us a picture of cosmic evolution. The early universe was a wilder, more active place. Galaxies were forming, growing, colliding. Gas was abundant. Quasars blazed as supermassive black holes gorged themselves on available material. Over billions of years, this activity declined. Galaxies settled into their current configurations. Star formation slowed. The fuel supplies dwindled. The quasar epoch ended, and we entered the modern era of mostly quiet galaxies with dormant black holes. But here's where things get even more interesting. Recent observations, particularly from the James Webb Space Telescope, have revealed that studying quasars also allows us to test fundamental physics. In particular, they allow us to observe an effect called time dilation, one of the predictions of Einstein's theory of general relativity. According to relativity, time itself is affected by the expansion of the universe. An observer in the distant past would experience time flowing normally from their perspective. 1 second would feel like 1 second. But when we observe that distant epoch from our present vantage point, looking back across billions of years of cosmic expansion, we should see events unfolding in slow motion. This is cosmological time dilation, and it's a direct consequence of the fact that space itself has been expanding. For decades, astronomers have tested this prediction using supernova explosions in distant galaxies. Supernovae brighten and then fade following a predictable pattern. When you observe distant supernova, those at high redshift, you find that their light curves, the graphs of brightness versus time, appear stretched out. A supernova that would brighten and fade over the course of, say, 3 weeks if it were nearby, will appear to take much longer if it's at high redshift. The effect matches Einstein's predictions beautifully, but extending this test to the highest redshifts to the earliest epochs of the universe has been challenging with supernovae alone. They're bright enough to see at great distances, but they're also transient, and catching them at the highest redshifts requires luck and extensive monitoring. Quasars, however, offer another avenue. Quasars vary in brightness over time, their accretion disks flickering and flaring as material spirals inward. And these variations form a kind of clock, a pattern that can be measured. In 2023, astronomers Geraint Lewis and Brendan Brewer published a remarkable study in Nature Astronomy. They analysed observations of nearly 200 quasars spanning a range of redshifts, including some at redshift greater than 7. By carefully studying the variations in these quasars' brightness across different wavelengths, from visible light into the infrared, and using sophisticated statistical techniques, they were able to standardize each quasar's variability pattern and measure how the expansion of the universe affected it. The results confirmed Einstein's prediction. Quasars in the distant universe showed variability patterns that appeared stretched out, running in slow motion compared to nearer quasars. A quasar at redshift 7, seen when the universe was less than 1 billion years old, showed variations that appeared to unfold 5 times more slowly than they would if that quasar were nearby. If you could somehow transport yourself back to that epoch and stand next to that quasar, setting aside all the practical impossibilities, you'd experience time flowing normally. But from our perspective, looking back across more than 13 billion years of expansion, we see time running at 1/5 speed. This is both a confirmation of fundamental physics and a profound reminder of what quasars represent. They're not just distant objects. They're windows into epochs when the universe itself was different, younger, smaller, denser, more active. The light reaching us from the earliest quasars has been travelling longer than Earth has existed. It began its journey before our solar system formed. These photons, stretched by expansion, redshifted into the infrared. carry information from a cosmos so different from our present-day universe that it challenges imagination. And we've only begun to explore the most distant quasars. The James Webb Space Telescope, operational since 2022, has revolutionized our ability to study the earliest epochs. JWST's unprecedented sensitivity in the infrared allows it to detect and characterize quasars at redshifts that were previously unreachable. In just the first few years of operation, JWST has observed quasars in exquisite detail, revealing properties of their accretion disks, their host galaxies, and their environments in ways that were impossible with earlier telescopes. These observations are raising new questions even as they answer old ones. How did supermassive black holes grow so massive so quickly? What were the first galaxies like? How did the interplay between quasar activity and galaxy formation shape the structures we see today? The ancient light from quasars is helping us address these mysteries, pushing our understanding of cosmic history into earlier and earlier times. But quasars don't just shine esotropically, spreading their light evenly in all directions. Some quasars display another remarkable feature, one that extends far beyond the central accretion disk and involves some of the most extreme physics in the universe. Relativistic jets of material shooting outward at nearly the speed of light, powered by magnetic fields of incredible strength. These jets deserve our attention because they reveal yet another aspect of the quasar phenomenon. Jets, light-years-long beams of raw energy. When Cyril Hazard and his colleagues at Australia's Parkes Radio Telescope used lunar occultations to precisely locate 3C273 in 1962, they discovered something peculiar. The radio emission from this object didn't come from a single point. Instead, there were two distinct radio sources very close together. When optical observations followed, astronomers found that one of these radio sources corresponded to the bright central object that Schmidt would later identify as the quasar itself. But the other source aligned with something even stranger. A faint jet of luminous material extending from the quasar. This was humanity's first glimpse of an extragalactic relativistic jet, and it would turn out that jets are a common, perhaps even universal, feature of quasars and other actively accreting supermassive black holes. They're among the most spectacular phenomena in astrophysics, combining elements that push physics to its limits: matter moving at substantial fractions of light speed, magnetic fields millions of times stronger than Earth's, particle acceleration to energies that dwarf anything achievable in our most powerful accelerators, and structures that extend for hundreds of thousands or even millions of light years from their source. Let's start with the basics. A jet, in the context of a quasar, is a narrow beam of material ejected perpendicular to the accretion disk. Typically, jets come in pairs, shooting outward in opposite directions along the rotation axis of the black hole and accretion disk system. The material in these jets can move at 95% of light speed or faster. At these velocities, the effects of special relativity become pronounced. Time dilates, lengths contract, and the jet's momentum and energy calculations require relativistic physics rather than the simpler Newtonian mechanics that works for slower moving objects. How do jets form? This is one of the outstanding questions in astrophysics, and despite decades of work, we still don't have a complete answer. But the basic ingredients are understood. You need an accretion disk, a spinning black hole, and, crucially, magnetic fields. As material spirals inward through the accretion disk, it's not just pulled by gravity, it's also permeated by magnetic fields. These fields exist because the plasma in the disk conducts electricity, and moving electrically charged particles generate magnetic fields. The disk's rotation twists and tangles these fields, creating a complex magnetic structure. In the inner regions near the black hole, the magnetic fields can become extremely strong and highly organized. One theoretical mechanism, proposed by Roger Blandford and Roman Zanayak in 1977, suggests that magnetic field lines threading the event horizon of a spinning black hole can extract rotational energy from the black hole itself. The black hole's spin drags space-time around with it, an effect called frame dragging. This rotation can twist magnetic field lines anchored in the accretion disk, and as these field lines wind tighter, they can accelerate particles along the rotation axis, launching them outward in collimated jets. This is the Blandford-Znajek process, and it's thought to be a key mechanism for powering the most energetic jets. The disk itself also contributes. As magnetic fields wind up due to the disk's differential rotation, inner regions spinning faster than outer regions, they build up magnetic pressure. This pressure can force material out of the disk, but the path of least resistance is perpendicular to the disk, along the rotation axis. Material that tries to escape in other directions encounters the dense material of the disk itself. Material ejected along the poles, on the other hand, can escape more freely. The magnetic field, twisted into a helical shape by the rotation, acts like a nozzle, focusing and accelerating the outflow into narrow jets. Computer simulations of this process are extraordinarily complex. You need to model magnetohydrodynamics, the behavior of electrically conducting fluids in magnetic fields, in the context of general relativity, accounting for the extreme space-time curvature near the black hole. You need to track how particles are accelerated, how they radiate, how the radiation interacts with the magnetic field. Even with powerful supercomputers, fully simulating jet formation from first principles remains at the edge of what's possible. But the simulations that have been done support the basic picture. Twisted magnetic fields in the accretion disk and ergosphere of a spinning black hole can launch jets. Once launched, these jets can extend for astonishing distances. Observations with radio telescopes have traced jets from quasars out to scales of hundreds of thousands of light-years. Some jets exceed 1 million light-years in length. To put that in perspective, a jet that long, if it started at the centre of our Milky Way, would extend well beyond our galaxy's edge and reach into the space between galaxies. These structures are visible because particles within the jets, primarily electrons and positrons, are accelerated to extremely high energies and emit synchrotron radiation as they spiral around magnetic field lines. This radiation is brightest at radio wavelengths, which is why radio telescopes are so effective at studying jets. But jets don't just emit radio waves. Depending on the particle energies and the environment through which the jet travels, jets can shine across the electromagnetic spectrum. Some jets are bright in optical light. Others emit X-rays. A few especially energetic jets have been detected emitting gamma rays, the highest energy photons we know of. Each wavelength tells us something different about the physics at work. The fact that jets are collimated, that they remain narrow over such vast distances, is itself remarkable and not yet fully understood. You might expect a beam of material shooting out at near-light speed to spread out, to gradually widen as it travels, and jets do widen somewhat, but they remain surprisingly narrow, suggesting that something is confining them. Magnetic fields are the leading candidate. The helical magnetic structure that launched the jet continues to exert what's called magnetic hoop stress, a confining force that keeps the jet focused. The interaction between the jet and the surrounding intergalactic medium might also play a role, with the external gas pressure helping to collimate the outflow. Within the jets, particles reach incredible energies. We're talking about electrons accelerated to energies exceeding trillions of electron volts, far beyond what the Large Hadron Collider, our most powerful particle accelerator, can achieve. The mechanisms for this acceleration are thought to involve shockwaves travelling down the jet, regions where the jet's smooth flow breaks down into turbulence, and magnetic reconnection events where tangled magnetic field lines suddenly snap and reorganize, releasing tremendous amounts of energy in the process. A 2020 study published in Nature Communications examined gamma-ray flares from a quasar designated 3C279, one of the brightest blazars. We'll get to what blazars are shortly. The researchers found variability patterns in the gamma-ray emission that occurred on timescales of just minutes. Such rapid changes pointed toward magnetic reconnection as the acceleration mechanism. When magnetic field lines in the jet reconnect, they can dump vast amounts of magnetic energy directly into particle acceleration, creating sudden bursts of high-energy emission. It's the same basic process that powers solar flares on our sun, but scaled up to almost incomprehensible levels. Observations with X-ray telescopes like Chandra have provided additional insights into jets. By measuring the X-ray spectrum from different regions along a jet, astronomers can estimate the magnetic field strength, the speed of the jet material, and the energy being carried. One particularly interesting finding is that the kinetic energy transported by jets, the energy carried by the moving particles, can rival or even exceed the total radiative luminosity of the quasar itself. In other words, the quasar isn't just shining brightly, it's also launching jets that carry comparable amounts of energy outward. This suggests that jets are a major factor in the overall energy budget of the black hole accretion process. Jets don't just affect the immediate environment of the quasar, they have far-reaching impacts on their host galaxies and even on the intergalactic medium. As a jet ploughs through surrounding gas, it heats that gas, sometimes blowing it away entirely. This process, called feedback, can regulate star formation in the host galaxy. If a jet heats or ejects the cold gas that would otherwise collapse to form stars, it effectively shuts down star formation. Observations suggest that this quasar feedback may be one of the reasons why the most massive galaxies in the universe contain relatively few new stars. Their central black holes during their active quasar phase may have blown away much of the gas needed for continued star formation. When jets reach the edges of their host galaxies and encounters the thin gas of the intergalactic medium, they can inflate enormous bubbles or lobes of hot magnetized plasma. Radio observations show these lobes around many quasars and radio galaxies, glowing with synchrotron radiation. The lobes can persist for millions of years after the quasar itself has faded, a kind of fossil record of past jet activity. Some jets terminate in hotspots, bright regions where the jet's forward motion is slowed by colliding with dense gas, creating a standing shockwave. Others show intricate structure, knots and filaments of enhanced brightness suggesting variations in the jet's speed or direction over time. Each of these features offers clues to the physics of jet propagation and the environments through which jets travel. And then there are blazars, a special class of quasars where one of the jets happens to point almost directly at Earth. This is where things get truly extreme from an observational standpoint. Blazars, when jets point at Earth. Imagine a quasar in the distant universe, its accretion disk blazing with the light of trillions of suns, its jets shooting outward perpendicular to that disk at 95% of light speed. Now imagine that, purely by chance, one of those jets happens to be aimed almost directly toward Earth. What would we see? We'd see a blazar, and blazars are among the most extreme objects in the observable universe, not because they're fundamentally different from other quasars, but because of a quirk of geometry combined with the strange effects of special relativity. When matter moves toward you at a significant fraction of light speed, several relativistic effects come into play. The first is called relativistic beaming. light emitted by the moving material gets concentrated into a narrow cone pointing in the direction of motion, much like water from a hose appears to spray farther when you're running forward. For a jet moving at 95% of light speed, this beaming effect is dramatic. Most of the jet's radiation is focused into a cone only a few degrees wide. If you're inside that cone, if the jet happens to be pointing at you, you see vastly enhanced brightness. If you're outside the cone, you see much less. The second effect is Doppler boosting. Just as the pitch of a siren changes depending on whether the ambulance is moving toward or away from you, the energy of photons changes depending on the motion of their source. Photons from a source moving toward you are blue shifted to higher energies. Photons from a source moving away are red shifted to lower energies. For a relativistic jet, this effect is substantial. Photons that might have been emitted as radio waves can be Doppler boosted into the visible or even ultraviolet range. X-ray photons can become gamma rays. The combination of relativistic beaming and Doppler boosting means that a blazar, a quasar whose jet points at us, appears far brighter than it would if we viewed it from the side, and the radiation we receive is shifted to higher energies, making blazars powerful sources of X-rays and gamma rays. Additionally, because we're looking directly down the jet, seeing material moving toward us at near light speed, the light travel time effects become apparent. Different parts of the jet can appear to move sideways across the sky at speeds greater than light speed, not because anything is actually exceeding light speed, but because of the projection effect combined with the finite speed of light. This is called superluminal motion, and it was one of the early pieces of evidence that jets contain material moving at relativistic velocities. Blazars vary rapidly in brightness. Because we're looking down the jet, we see the effects of changes in the jet structure or particle population almost as soon as they occur. There's no smearing effect from light travel time across the jet's width, as there would be if we viewed it from the side. This means blazars can flare from faint to bright in hours or even minutes. Their spectra lack the strong emission lines typical of other quasars, because the jet's intense, rapidly varying radiation overwhelms the light from the accretion disk and the surrounding gas that would normally produce those lines. One famous blazar is 3C279, located in the constellation Virgo, interestingly, in the same general region of sky as 3C273, though much more distant. 3C279 has a redshift of about 0.54, placing it roughly 5 billion light-years away. It was one of the first sources detected by the Fermi Gamma Ray Space Telescope, and it has been studied extensively across all wavelengths. In 2020, as mentioned earlier, researchers studying 3C279's gamma ray emission noticed something fascinating. The gamma ray light curve showed a distinctive pattern. Shorter flares nested inside longer ones like waves upon waves. This peak-in-peak variability, occurring on timescales of minutes, pointed toward magnetic reconnection in the jet as the acceleration mechanism. The researchers calculated that this reconnection must be happening at distances of roughly 10,000 gravitational radii from the black hole, far enough that photons produced there can escape without being absorbed by colliding with other photons in the intense radiation environment near the accretion disk. Magnetic reconnection in jets involves the same basic physics as solar flares, but operates at far greater scales and energies. When magnetic field lines in the jet become tangled, perhaps due to turbulence generated by the kink instability, where the jet develops twists and bends like a kinked garden hose, they can suddenly realign, releasing magnetic energy. This energy goes into accelerating particles, which then radiate at high energies. The process can be remarkably efficient, converting a substantial fraction of the available magnetic energy into particle kinetic energy and then into radiation. The rapid variability of blazars tells us something important about jet structure. These variations indicate that jets aren't uniform, steady flows. They're turbulent, with regions of enhanced particle density and magnetic field strength, with shock waves propagating along their length, with reconnection events occurring sporadically. The smooth, arrow-straight jets we often see in images are actually seething with small-scale structure and activity. Studying blazars also helps address a long-standing question about quasar jets. What produces the X-rays we observe from them? There are two main possibilities. One is that the X-rays come from inverse Compton scattering, where high-energy electrons in the jet collide with low-energy photons, particularly photons from the cosmic microwave background, and boost those photons to X-ray energies. If this is correct, it implies that the jet must be highly relativistic, with Lorentz factors, the factor by which time dilates and lengths contract, of 20 or more, even at distances of hundreds of thousands of light-years from the black hole. The alternative is that the X-rays are synchrotron radiation from a separate population of extremely high-energy electrons in the jet. This would require accelerating electrons to energies exceeding 100 trillion electron volts, extraordinarily high, but perhaps achievable through multiple stages of acceleration, involving shock waves and magnetic reconnection. Recent observations, including optical polarimetry studies with the Hubble Space Telescope, tend to favour the synchrotron interpretation for many jets, though the debate continues and different jets may be dominated by different processes. Blazars also serve as laboratories for testing physics in extreme conditions. When gamma rays from a distant blazar travel through the universe toward us, they can interact with the diffuse intergalactic radiation, the starlight and ultraviolet emission from galaxies, the infrared emission from dust. High-energy gamma rays can collide with these lower-energy photons and annihilate, creating electron-positron pairs. This absorption leaves a signature in the spectrum of the arriving gamma rays. By studying this signature, astronomers can probe the intergalactic radiation field, learning about star formation rates and galaxy evolution across cosmic history. Blazars are also being used in the search for violations of Lorentz invariance, a fundamental symmetry of physics. According to special relativity, the laws of physics should be the same in all inertial reference frames, and the speed of light should be constant. But some theories of quantum gravity predict that at extremely high energies, this symmetry might break down ever so slightly. If that's true, gamma rays of different energies from a distant blazar might arrive at Earth at slightly different times, even though they were emitted simultaneously. So far, observations haven't detected any such effect, placing tight constraints on possible violations of Lorentz invariance. The study of blazars, then, does more than just reveal the properties of quasar jets. It connects to fundamental physics, to the structure of space-time itself, and it reminds us that the universe is full of natural laboratories where conditions far exceed anything we can create on Earth, where nature conducts experiments we could never perform ourselves. But let's step back now from the specific physics of jets and blazars, back to the bigger picture of quasars and what they tell us about cosmic history. Because some of the most exciting developments in quasar astronomy in recent years have come from pushing observations to the highest redshifts, to the most distant quasars, the ones that show us the universe in its first few 100 million years. And these observations have revealed surprises that are challenging our understanding of how supermassive black holes form. Discovering the most distant quasars, the first billion years. There's something almost paradoxical about the most distant quasars. They're among the oldest objects we can observe. We see them as they were more than 13 billion years ago, when the universe was a small fraction of its current age. Yet they contain supermassive black holes with masses of hundreds of millions or even billions of solar masses. And that's the puzzle. How did these black holes get so massive so quickly? Black hole growth takes time. A black hole grows by accreting matter from its surroundings, and there are physical limits to how fast this can happen. As matter falls toward a black hole and heats up, it radiates light. That radiation exerts pressure, pushing outward on the infalling matter. At a certain luminosity, called the Eddington luminosity, the outward radiation pressure exactly balances the inward gravitational pull. Above this limit, radiation pressure would blow away the infalling matter faster than it could be accreted. For a black hole to grow, it generally can't exceed the Eddington limit for prolonged periods. The Eddington limit implies a maximum growth rate. Even if a black hole accretes matter continuously at the Eddington rate, the fastest sustainable rate, it can only grow exponentially with a characteristic timescale of about 45 million years. Start with a stellar mass black hole of say 10 solar masses and let it accrete at the Eddington limit. After 45 million years, it would have doubled in mass to 20 solar masses. After another 45 million years, 40 solar masses. After 10 doubling times, 450 million years, it would reach roughly 10,000 solar masses. That's still far short of the billion solar mass black holes we see in the most distant quasars. To make matters worse, those distant quasars are seen at redshifts of 6, 7 or higher, corresponding to times less than 1 billion years after the Big Bang. So we need black holes to grow from stellar masses, or even smaller if they formed from the very first stars, to billions of solar masses in less than 1 billion years. That's a tight constraint. It requires either that the black hole started with much larger seed masses than we'd expect from stellar collapse, or that they accreted at super Eddington rates, or that something else entirely is going on. Enter the James Webb Space Telescope, JWST, launched in December 2021 and operational since mid-2022, has revolutionized the study of the early universe. Its large mirror, its position far from Earth at the second Lagrange point, and especially its sensitivity in the infrared, allow it to see farther and more clearly than any previous telescope. And because the light from the most distant objects is redshifted into the infrared by cosmic expansion, JWST is perfectly suited to studying the highest redshift quasars. One of JWST's early science programs focused on a quasar designated J112 0+0641. At the time observations were planned, this was the most distant known quasar, with a redshift of about 7, meaning we see it as it was roughly 13 billion years ago. The quasar's black hole has a mass exceeding 1 billion solar masses. How it grew so large so quickly was a mystery. Earlier observations had provided some information, but JWST's mid-infrared instrument, or MIRI, offered unprecedented capability to study the quasar's spectrum in detail. When the JWST data were analysed, led by researcher Sarah Bosman, the results were surprising. Not because they showed something exotic, but because they showed that the quasar looked normal. The spectrum indicated that the accretion disk around the black hole was operating just like accretion disks around lower redshift quasars. The composition of the gas, the temperature structure, the efficiency of accretion, all were comparable to what we see in more recent quasars. There was no sign of unusual physics, no indication that the early universe black holes were somehow special in their feeding mechanisms. This finding, published in Nature Astronomy in 2024, actually made the puzzle harder to solve. If early quasars weren't accreting matter more efficiently than modern ones, then how did their black holes grow so fast? The evidence increasingly pointed toward the idea that these black holes must have formed with large initial masses, the so-called heavy seed or primordial black hole scenario. According to this idea, in the very early universe, Perhaps within the first few 100 million years after the Big Bang, massive clouds of primordial gas composed almost entirely of hydrogen and helium with virtually no heavier elements, could collapse directly into black holes without first forming stars. Under the right conditions, if a gas cloud is massive enough and hot enough to resist fragmentation into smaller clumps, it might collapse into a black hole with a mass of tens of thousands or even hundreds of thousands of solar masses right from the start. Give such a black hole 1 billion years to grow, with accretion at or slightly above the Eddington limit, and you could plausibly reach the billion solar mass black holes we observe in the most distant quasars. Computer simulations by researchers at the University of Portsmouth and elsewhere have explored how this might work. They find that within a few 100 million years after the Big Bang, vast streams of cold gas could flow together along dark matter filaments, the cosmic web structure that underlies the distribution of matter in the universe. Where these streams converge, dynamically unstable clouds could form. These clouds, with tens of thousands of solar masses, might collapse not into stars but directly into intermediate mass black holes. These black holes would then act as seeds, growing into the supermassive black holes that power quasars. It's an elegant solution to the problem, though not without its own questions. How common were these direct collapse events? What fraction of supermassive black holes formed this way versus growing from stellar mass seeds? And why do some galaxies have supermassive black holes while others don't? JWST is helping to address these questions by observing more and more distant quasars and characterizing their properties. In 2024, several teams reported results from JWST surveys designed to find and study early quasars. One study, led by Anna Christina Eilers at MIT, looked at 5 quasars that formed between 600 and 700 million years after the Big Bang. The team used JWST to examine not just the quasars themselves, but their surrounding environments, the number of neighbouring galaxies, the distribution of matter around them, and here they found another surprise. According to prevailing theories, supermassive black holes should form in the densest regions of the universe, where dark matter and gas concentrate, where galaxy formation is most vigorous. These high-density regions should be surrounded by many other galaxies, providing both a rich environment for black hole growth and observable evidence of that high density. But when Eilers and her colleagues looked at the fields around these 5 early quasars, they found considerable diversity. Some quasars were indeed in crowded fields, surrounded by dozens of neighbouring galaxies, just as theory predicted. But others appeared to be in relatively empty regions, with only a handful of nearby galaxies visible. Some of them seemed to be sitting in the middle of nowhere, Eilers commented in press coverage of the work. How can a supermassive black hole grow to billions of solar masses if there's not much matter around to feed it? This is a challenge for our models. It's possible that the lonely quasars aren't as isolated as they appear. Perhaps the neighbouring galaxies are there but heavily obscured by dust, making them difficult to detect even with JWST. Or perhaps there are pathways for black hole growth that we haven't fully considered, ways for gas to be funneled to black holes even in relatively sparse environments. Another JWST program, called Cosmos Web, is surveying a larger area of sky to find additional high redshift quasars and build up statistics. By late 2024, this survey and others had identified dozens of quasar candidates at redshifts greater than 6, more than doubling the number of known quasars from the first billion years of cosmic history. Each of these objects provides another data point, another piece of the puzzle. Studies of these distant quasars are also revealing information about the host galaxies themselves. Earlier observations had struggled to separate the light of the quasar from the light of its surrounding galaxy. The quasar is so bright that it overwhelms the galactic starlight. But JWST's sensitivity and resolution have allowed astronomers to detect and measure the starlight from quasar-host galaxies for the first time at high redshifts. A study presented at a JWST science meeting in 2023 reported detecting starlight from host galaxies around 6 quasars at redshifts above 6.5. The galaxies appeared to be compact, only a few thousand light-years across, and massive, containing enough stars to account for tens of billions of solar masses. Interestingly, the mass of these galaxies seemed disproportionately large compared to the black hole masses, suggesting that at these early times galaxy growth might have been slightly ahead of black hole growth, opposite to what's sometimes seen in the local universe. All of these findings paint a picture of the early universe as a complex dynamic place. Galaxies were forming rapidly, black holes were growing quickly, and the interplay between these processes was shaping the structures we see. Quasars from this epoch are giving us our best view of this critical period, this cosmic dawn when the universe transitioned from the Dark Ages, the time after the cosmic microwave background was emitted but before the first stars formed, to an era of light and structure. And there's more to come. JWST is just beginning its mission. Scheduled to observe for at least a decade and possibly much longer, it will continue to push deeper into the early universe, finding more distant quasars, characterizing their properties, and constraining the models of how supermassive black holes and galaxies form and evolve. Each new observation has the potential to surprise us, to challenge our understanding, to reveal aspects of the early universe we hadn't anticipated. The story of quasar discovery and study, then, is ongoing. From Schmidt's 1963 revelation that these star-like objects were actually incredibly distant and luminous, through decades of work to understand their physics, to the cutting-edge observations being made right now with the most advanced telescopes humanity has ever built, quasars continue to fascinate and inform. They're more than just interesting objects. They're tools for probing the universe, lighthouses that illuminate the cosmic past. Which brings us finally to a place of reflection. What do quasars mean to us? Not just as scientists studying the universe, but as conscious beings contemplating our place in this vast ancient cosmos. What can we take away from the story of these distant beacons? The cosmic lighthouse. Analogy. Meaning and reflection. Picture a lighthouse on a rocky coast, its beams sweeping across the darkness, visible from miles out to sea. For ships navigating through the night, that lighthouse is more than just a light. It's a guide, a reference point, a source of critical information about where the coastline lies. Quasars serve a similar function for astronomers navigating the vastness of cosmic space and time. They're beacons that illuminate the distant universe, marking the positions of galaxies billions of light-years away, showing us what those galaxies were doing in epochs we could never otherwise study. But the analogy goes deeper. A lighthouse beam, sweeping regularly, marks the passage of time. Sailors can use it to track their position, to measure their progress. Quasars, with their variability and their cosmological redshifts, similarly mark cosmic time. As we've discussed, observations of quasar variability have allowed astronomers to measure time dilation in the early universe, confirming Einstein's predictions. Quasars are literally cosmic clocks, their flickering brightness encoding information about the flow of time across billions of years of expansion. And like lighthouses that tell us about coastal geography, quasars tell us about cosmic geography. The distribution of quasars across the sky and across redshift space maps out how matter was arranged in the early universe. Surveys of thousands of quasars reveal the large-scale structure of the cosmos, the filaments and voids of the cosmic web, the clustering of galaxies, the evolution of structure from the relatively smooth conditions shortly after the Big Bang to the clumpy, galaxy-filled universe we inhabit today. But perhaps the most profound aspect of the lighthouse analogy is this. Quasars show us not just where things are, but what they're becoming. Every quasar we observe is a galaxy in a particular phase of its evolution, a phase characterized by vigorous activity, by a supermassive black hole gorging on available fuel, by jets that may be heating and expelling gas, by star formation rates that can be prodigious or suppressed depending on the details of the quasar's environment. We're witnessing transformation, the process by which young, gas-rich galaxies turn into the more mature, evolved galaxies we see nearby. Our own Milky Way almost certainly went through a quasar phase. The evidence is indirect but compelling. First, we have a supermassive black hole at our galactic centre, Sagittarius A star, with its 4 million solar masses. The black hole is there, it's just not currently active. Second, observations of the Milky Way from outside, if such a perspective were possible, show evidence of past activity. In 2010, astronomers using the Fermi Gamma Ray Space Telescope discovered enormous lobes of high-energy emission, extending above and below the plane of our galaxy, each lobe stretching about 25,000 light-years from the galactic centre. These structures, called Fermi bubbles, are visible at gamma-ray and X-ray wavelengths. They appear to be the result of a massive outburst from the galactic centre sometime in the past, possibly as recently as a few million years ago, though estimates vary. Did this outburst constitute a quasar phase? Probably not at the peak luminosity we associate with the most powerful quasars, but perhaps a more modest active phase. The black hole may have consumed a particularly large amount of gas, perhaps from a passing cloud or the tidal disruption of a star, and temporarily brightened. The Fermi bubbles are the fossil record of this event, hot plasma blown outward from the galactic centre, still glowing millions of years later. Looking further back in time, it's likely that the Milky Way was a true quasar when the universe was younger, when there was more gas available, when our galaxy was still assembling. The quasar would have eventually faded as the fuel supply diminished. What remained was the galaxy we know today, with its disk of stars and gas, its central bulge, its spiral arms, its relatively quiescent black hole. And the future. There's an intriguing possibility. The Andromeda Galaxy, our nearest large galactic neighbour, is currently approaching the Milky Way at about 75 miles per second. In approximately 4 to 5 billion years, Andromeda and the Milky Way will collide. When two galaxies merge, their gas gets stirred up, compressed, and funneled toward the centres of both galaxies. If enough gas makes it to the central black holes, and the black holes themselves will eventually merge, there could be a renewed burst of quasar activity. Our quiescent galaxy might briefly become a quasar again, shining across the cosmos for a few million years before settling back into dormancy. Of course, humanity will likely be long gone by then, and Earth itself might not survive the red giant phase of the Sun, which will occur in about 5 billion years, around the same time as the Andromeda collision. But it's fascinating to contemplate nonetheless. The idea that galactic evolution is cyclic, that quasar phases can recur. The broader lesson is one of cosmic cycles and evolution. The universe changes, galaxies form, grow, merge, black holes accumulate mass, shine brightly, fade. Star formation ramps up and winds down. The universe at a redshift of 7, seen when it was less than 1 billion years old, was a dramatically different place from the universe today. Quasars were common. Galaxy collisions were frequent. The cosmic microwave background was hotter. The first generation of stars was just beginning to enrich the universe with heavier elements. Over 13 billion years, the universe has expanded, cooled, and evolved. The quasar epoch has passed. We live in a calmer era where most supermassive black holes are quiescent, where galaxy collisions are relatively rare, where the universe is dominated by dark energy that drives an accelerating expansion. But the light from those ancient quasars is still reaching us, and it carries messages from that earlier, more turbulent time. When you look at an image of a distant quasar, you're not just seeing an astronomical object, you're looking at a time capsule. The light entering your eyes or the telescope's detector began its journey when the universe was young, when the structures around us were just forming, when the cosmic story was still in its early chapters. Every photon from a high redshift quasar has travelled across billions of light years of expanding space, its wavelength stretched by that expansion, finally arriving to tell us about conditions in the distant past. There's a privilege in that, a remarkable gift. We live at a time when technology allows us to study the universe across its full history. We can observe the cosmic microwave background, seeing the universe as it was just 380,000 years after the Big Bang. We can observe distant quasars, seeing galaxies and black holes as they were in the first billion years. We can observe nearby galaxies, seeing the universe as it was relatively recently. And we can study our own Milky Way, probing the present-day cosmos in exquisite detail. This range of perspectives, this ability to look back across time, is unprecedented in human history. Earlier generations could only speculate about the universe's past. We can observe it, and what we observe is a story of change, of evolution, of a universe that's dynamic and alive in a metaphorical sense. Stars are born and die. Galaxies collide and merge. Black holes grow and shine. Over cosmic timescales, everything changes. We're part of that story briefly. A species that arose on a planet orbiting an ordinary star in an ordinary galaxy. But a species that has gained the ability to look outward and backward, to piece together the narrative of how we came to be. Quasars remind us of scale, the immense scale of the universe in space and time. They remind us of physics operating under extreme conditions. They remind us that we don't yet understand everything, that mysteries remain, that each answer leads to new questions. And they remind us, perhaps most fundamentally, that we're connected to the cosmos in ways both literal and profound. The atoms in our bodies were forged in stars. The photons reaching our eyes from distant quasars connect us, however tenuously, to the early universe. We're not separate from the cosmos, we're part of it, products of its evolution, observers fortunate enough to contemplate its wonders. Unanswered questions and ongoing mysteries. For all that we have learned about quasars over the past 6 decades, much remains uncertain. Science is fundamentally a process of asking questions, proposing answers, testing those answers, and discovering new questions in the process. Quasar astronomy is no exception. Let's consider some of the major open questions that researchers are currently grappling with. How exactly do jets form? We've discussed the basic ingredients: accretion disks, magnetic fields, black hole spin, and we've mentioned mechanisms like the Blandford-Znajek process. But the devil, as they say, is in the details. Computer simulations of jet formation are extraordinarily complex and still don't capture all the relevant physics. Exactly how magnetic fields get amplified and organised in the inner accretion disk, exactly how particles get injected into the jet and accelerated to relativistic energies, exactly what determines the collimation and stability of jets over vast distances. These are questions that require both better observations and more sophisticated modelling. Different jets may also operate differently. Some jets are predominantly electron-positron plasma. Others may contain a significant fraction of protons and heavier ions. Some jets are very straight and stable. Others show bends, kinks, and complex morphology. Do these differences reflect different black hole spins, different accretion rates, different magnetic field configurations, or different environments. Disentangling these factors is an ongoing challenge. How did the first supermassive black holes form? As we discussed, the existence of billion solar mass black holes less than 1 billion years after the Big Bang is difficult to explain with standard models. The heavy seed scenario, direct collapse of primordial gas clouds into intermediate mass black holes, is currently the favoured explanation, but it's not without problems. We don't yet have direct observational evidence of these intermediate mass seeds. We don't fully understand what conditions would allow direct collapse versus fragmentation into stars, and we don't know how common direct collapse was compared to other formation pathways. Future observations with JWST and other telescopes may help. If we can find and study quasars at even higher redshifts, seeing black holes that are still in the process of assembling, we might be able to constrain formation models. If we can measure the masses of black holes in a large sample of early galaxies, we might be able to see a progression from smaller to larger masses, offering clues to growth mechanisms, and if we can observe the host galaxies in more detail, we might identify characteristics that correlate with black hole mass, shedding light on the relationship between galaxy and black hole growth. Why are some early quasars in sparse environments? The lonely quasars discovered by Eilers and colleagues challenge our understanding. If black holes need gas to grow, and if gas tends to concentrate in high-density regions along with galaxies, then how can quasars exist in apparent voids? Are these quasars really isolated, or are we missing obscured galaxies nearby? If they're truly isolated, does that mean gas can be channeled over large distances, perhaps along dark matter filaments that aren't currently visible to us? Or does it mean that black holes can grow more efficiently than we thought, perhaps through super-Eddington accretion, or episodic feeding events? Answering these questions will require more observations, particularly deeper and more sensitive surveys that can detect faint dusty galaxies around quasars. It will also require improved simulations that can model gas flow on scales from the cosmic web down to the immediate vicinity of the black hole. What is the relationship between quasars and their host galaxies? We know that supermassive black holes and their host galaxies co-evolve. The masses of black holes tend to correlate with properties of the galaxies, like the mass of the central bulge. But we don't fully understand the causal relationships. Does the black hole regulate galaxy growth through feedback, shutting down star formation by heating or expelling gas? Or does galaxy growth regulate black hole growth by controlling how much gas reaches the central regions? Or is the relationship more complex, with feedback operating in both directions and varying over cosmic time? Recent observations suggesting that black holes in the early universe might be more massive relative to their host galaxies than expected complicate this picture. If early black holes grew faster than their galaxies, what changed over time to bring the black hole to galaxy mass ratio to the values we see in the local universe? Was there a transition point, an epoch when galaxy growth caught up? Understanding this co-evolution is crucial for modelling how galaxies assemble and how the universe's structure developed. What role do quasars play in reionization? The epoch of reionization, roughly 250 million to 1 billion years after the Big Bang, marks the time when the neutral hydrogen that filled the universe was ionized by ultraviolet light from the first stars and galaxies. Quasars, with their copious ultraviolet emission, likely contributed to this process, though the dominant contribution probably came from massive stars in early galaxies. But quantifying the quasar contribution requires knowing how many quasars existed at that time, how bright they were, and how much of their ultraviolet light escaped into the intergalactic medium without being absorbed by local gas and dust. These are all active areas of research. Can we use quasars to probe dark matter and dark energy? Quasars serve as distant light sources whose light travels through the universe to reach us. As that light passes through intervening gas clouds, it gets absorbed at specific wavelengths, producing what are called Lyman alpha forest absorption lines in quasar spectra. By studying these absorption lines in many quasars, astronomers can map out the distribution of gas in the universe across cosmic time, and since gas traces dark matter, this gives us information about dark matter's distribution. Quasars are also being used in cosmological studies aimed at measuring the expansion history of the universe and constraining the properties of dark energy. By using quasars as standard candles, objects of known luminosity that allow distance measurements, or by studying the clustering of quasars across redshift, researchers can test cosmological models. This is a challenging endeavour because quasars aren't perfect standard candles, but progress is being made. These unanswered questions aren't signs of failure, they're signs of a vibrant, active field where discoveries continue to reshape our understanding. Each new telescope, each new observing campaign, each new theoretical insight brings us closer to answers. But it also inevitably raises new questions. That's the nature of scientific progress. The universe is vast and complex, and our understanding of it is an ongoing process, a journey rather than a destination. And as we continue that journey, as we peer deeper into the cosmos and farther back in time, quasars will remain among our most valuable guides. These cosmic lighthouses, blazing across billions of light years, illuminate the path toward understanding. Drifting towards sleep with ancient photons. Let's bring this journey home now, gently, as the ideas settle and the cosmos expands around us in imagination and reality both. Somewhere in the constellation Virgo, that faint point of light designated 3C27, 3 continues to shine. Right now, tonight, photons are streaming from its accretion disk, beginning the 3 billion year journey across space. 3 billion years from now, if anyone is here to observe them, those photons will arrive at Earth, carrying information about the quasar state in our present day. But we won't be here to see it. Our present is the quasar's distant future, and its present is our distant past. And scattered across the sky, thousands upon thousands of other quasars shine in their own epochs, their light racing toward us at the speed of light, some of it arriving tonight, entering telescopes, being recorded by detectors, studied by scientists, gradually revealing the universe's history. Each quasar is unique, its black hole mass, its accretion rate, its jet properties, its host galaxy, its environment. Yet each is also part of a larger pattern, a phase in the cosmic story when conditions allowed supermassive black holes to blaze with extraordinary luminosity. There's something almost poignant about quasars. They represent youth, vigour, abundance, galaxies in their wild adolescent phase before settling into the calmer adult state we see in the local universe. When we observe distant quasars, we're seeing galaxies that, if we could visit them today, would likely be quiescent. They're supermassive black holes dormant, their glory days long past. The light reaching us is evidence of what was, not what is. But that's true of all astronomical observation. We never see the universe as it is, we see it as it was, averaged over vast swathes of look-back time. And in that there's a kind of comfort. The universe has been here far longer than we have. It will be here far longer than we will. Our species is a brief flicker in cosmic time, a momentary arrangement of matter that happens to be conscious, curious, capable of understanding. We don't know what the deep future holds, the heat death as the universe expands forever perhaps, or some other fate we haven't imagined. But we know the past increasingly well thanks to observations of objects like quasars, those ancient photons that began their journey when the universe was young, when the first galaxies were forming, when supermassive black holes were feeding voraciously. Those photons have been travelling through the expanding cosmos for most of the universe's history. And tonight, some of them arrive. If you were to point a powerful telescope at certain patches of sky and collect enough light, you could detect photons from quasars at redshift 7, redshift 8, even higher. You could catch light that has been travelling since before Earth existed, since before the Sun formed, since before most of the stars in the Milky Way were born. There's profound privilege in that, and profound humility. We're lucky to live at a time and place where contemplating these matters is possible. Our planet is stable enough, our civilization technologically advanced enough, our atmosphere clear enough, mostly, that we can build telescopes and observe distant quasars. Not every planet in the universe offers that opportunity. Not every civilization, if there are others, reaches the point where they can study cosmology. We're fortunate. And we've learned so much from that February evening in 1963 when Maarten Schmidt paced his home, unable to contain his excitement over the shifted hydrogen lines, to the present day with JWST observing quasars from cosmic dawn. The story of quasar discovery and study is one of human curiosity and ingenuity. We identified these objects. We figured out what powers them. We're using them to map the universe, test physics, understand cosmic evolution. But for all we've learned, wonder remains. Perhaps that's the most important thing. Understanding doesn't diminish wonder. It enhances it. Knowing that a quasar is powered by a supermassive black hole with an accretion disk heated to millions of degrees doesn't make it less awe-inspiring. If anything, it makes it more so, because now we can appreciate not just the brightness, but the physical processes, the extremes of gravity and magnetism, the relativistic speeds, the vast distances and timescales involved. Lying here now, comfortable, safe, breathing the air of this small planet, you're connected to those distant quasars by the simple fact of existence in the same universe. The same physical laws that govern the accretion disk around a supermassive black hole, billions of light years away, also govern the chemistry of your body, the neurons firing in your brain as you process these words. It's all one cosmos, one grand system, and we're part of it. As you drift towards sleep, you might picture those quasars out there in the darkness, beacons in the cosmic night, their light streaming across the void. You might imagine the James Webb Space Telescope quietly orbiting the Sun at the second Lagrange point, its mirror collecting ancient photons, its instruments measuring wavelengths and creating spectra, sending data back to Earth where scientists will pore over it, asking questions, seeking answers. You might think about the next generation of telescopes already being planned. The extremely large telescope in Chile, the 30-meter telescope in Hawaii, future space telescopes even more capable than JWST, and the discoveries they'll make. The journey continues, the questions persist. The universe, vast and ancient, still holds countless secrets. Quasars have revealed many of them, but mysteries remain, and that's as it should be. A universe fully understood might be less interesting than one that continues to surprise us. So we observe, we theorize, we test, we learn, and occasionally we pause to appreciate the sheer magnificence of it all. The fact that we can know these things, that the universe is comprehensible, that light from the early cosmos carries information we can decode. Before I let you drift away completely into rest, I want to say thank you. Thank you for spending this time exploring quasars together, for letting your mind wander across billions of light years and billions of years of time. If you've enjoyed this journey through the cosmos, if Cosmovel's long-form explorations help you learn and relax, please consider subscribing to the channel and liking this video. It helps others find these cosmic conversations, and it lets me know that this work, researching, writing, recording, is worthwhile. The universe is vast, The questions are endless, but on this small planet, on this quiet night, you've spent time contemplating quasars, those blazing beacons from the early universe, and that's a beautiful thing. Rest well. Dream of distant light and ancient galaxies, of black holes and accretion disks, of jets stretching across hundreds of thousands of light years, of a cosmos that's far stranger and more magnificent than we ever imagined. And know that tomorrow when you wake, those quasars will still be out there, still shining, their light still travelling toward us, carrying messages from the distant past. The universe continues its vast, slow dance, and we're here to witness it, however briefly. Good night, and thank you for exploring the cosmos with Cosmo Vel.